In this lesson, we'll provide a summary of the CAP theorem for distributed computing, then discuss how the Hazelcast platform puts the theorem into practice. When you're writing an application that's accessing a data store, in most cases that application sees the data store as a single entity. The app requests a given piece of data, say an entry in a map, and the data store returns that data. The actual location of the data doesn't matter to the application as long as it gets the information it needs. Behind the scenes, however, is your Hazelcast cluster, which has distributed the contents of the map across all the cluster members. If your application requests a specific map entry, the cluster will respond with the data regardless of the physical location. The application doesn't know or care about the underlying system. We've discussed all the benefits of the distributed system in the Introduction to Hazelcast course. But a big consideration of any distributed system is the underlying reliability of the hardware and network that's supporting the cluster. We have to design the distributed system to handle a system or network failure. If the cluster member storing the data becomes unavailable, what do we do? The CAP theorem, also called Brewer's theorem, states that it is impossible for a distributed data store to simultaneously provide consistency, availability, and partition tolerance. Consistency means that a client requesting data will always receive the most up-to-date entry. If the system cannot guarantee that the entry is up to date, it will return an error. Availability means that the system will respond to a request with whatever data is available. However, there's no guarantee that the data is the most up-to-date data available. Partition tolerance means that the distributed data store itself will continue to operate even if there's packet loss, in other words, a network problem, between the members of the distributed system. Let's look at this theory in practice. We have a cluster of 3 members being accessed by 2 different clients. Under normal operations, both clients are reading and writing data to the cluster. If there's a network failure, the P in CAP says that the cluster keeps operating, even in a partitioned state. The clients are unaware of any issue with the data store, so they continue to write and read data normally. This can lead to data being out of sync between the partitioned cluster members. So in this case, when a client requests the map entry with the key of 3, what does the cluster do? Does it ensure consistency and return an error, since we cannot ensure that the data is the most up-to-date entry available? Or do we ensure availability and return the entry? The Hazelcast platform is designed primarily around availability. Most data structures will return an entry even if the cluster is partitioned, but there's no guarantee that the entry is the most recent data. To meet the need for consistency, earlier versions of Hazelcast IMDG provided distributed implementations of the Java concurrency primitives. Instead of returning data no matter what, these structures would return an error under partitioned conditions. You, the programmer, controlled your tolerance for possible old data by setting a minimum operating cluster size. Within the operating cluster, consistency was provided, but if the cluster fell below the configured limit, the data structure would return an error if called on. So in our previous partitioned example, if you configured the data structure with a minimum cluster member count of 2, Client A would continue to write to and read from the data structure, but Client B would receive errors. This condition would continue until the cluster was restored, at which point cluster operations would take over, resolve any data conflicts, and ensure that the consistent data structures were preserved across the entire cluster. Now we'll be honest, while this implementation worked in most situations, it did not pass the rigorous Jepsen testing process, which validates distributed data operations under a wide range of outage conditions. In some of those conditions, Hazelcast's consistently implementation did not behave as expected. One of the limitations was that the data contained by the consistency data structures was not itself validated across all the other cluster members. Although it was unlikely that an operational cluster would get out of sync, it was still possible due to the asynchronous method Hazelcast uses to replicate data across the distributed cluster members. Asynchronous is good enough for AP, but not for CP. In Hazelcast IMDG 3.12, we introduced the CP subsystem within the Hazelcast cluster. The CP subsystem maintains the linearizability of operations that write to or read from the data stored in the subsystem. Events happen one at a time in a linear fashion to ensure that there's one single known state, atomic state, for a given data entry at any given moment. The subsystem itself establishes and maintains consistency across the members using the Raft consensus algorithm. The Secret Lives of Data has an excellent animated tutorial that explains how Raft works to ensure consistency of data in a distributed system. If you would like to see this tutorial, click on the link on your screen. The Raft algorithm ensures that data is unavailable until it has been replicated to all cluster members, ensuring consistency across the cluster. If consistency cannot be ensured, the CP subsystem will not return a result to a client query. The CP subsystem passes those rigorous Jepsen tests. You can download the tests and view the results from the Jepsen GitHub repository. We'll discuss CP subsystem operations, including how consistency is guaranteed, in detail in the next lesson. Some key points to take away from this lesson. Distributed data systems are dependent on the underlying connectivity between members. These networks are never 100% reliable. There will at some point be a network outage that affects cluster operations. The CAP theorem discusses how a distributed data system will operate in this environment. Consistency means that the system returns only guaranteed data or an error. Availability means that the system always returns data. And partition tolerance means that the system has the ability to operate if the network fails. The Hazelcast platform is predominantly AP, preferring to return data whenever possible. Consistency APIs were available to provide a level of CP operation. In 3.12, we introduced the CP subsystem to provide true concurrency capabilities in the Hazelcast platform.